Hello and welcome back once again to the 8-bit computer. As I promised last time, today we'll be looking at this decimal display up here, which is showing the value in decimal of the 8 binary bits which are stored in the A register. And so the computer at this moment is running the same program that it has been running for the last few episodes, doing various mathematical operations. And so at some point in the program, for example here, there'll be move instructions or any other instructions which update the contents of the A register. And so when that happens, then the new value that is written into the A register shows up on this display here. And so today we'll have a look at how that works. And so I can stop the automatic clock here so we can just have a look at a single value. Now this decimal display works almost identically in the same way as the decimal display that Benito built for his 8-bit computer. And so I would strongly suggest that you have a look at his videos where he goes into the details of how this circuit is set up. We're using the same multiplexing technique that he uses. And one of the important parts of the circuit, of course, is this EEPROM chip here, this electrically erasable programmable read-only memory chip. And that chip will in fact send the particular decimal display signals that need to light up and the ones that need to not light up for displaying any particular binary value which is coming in on these green wires from the A register. And so that chip needs to be programmed to display these values correctly. And to be able to program it, I've built this EEPROM programmer, and it too is very similar to the one that Benito builds. And so I'll link some of his videos concerning his EEPROM programmer as well. And the main part of the EEPROM programmer is this Arduino Nano, which we use just as Ben does. And so we can insert an EEPROM chip in here, and then we need to write software for this Arduino Nano, which will then allow us through software to control which values are written into which addresses of the EEPROM chip, which we have here. And so I'd say the biggest difference between my decimal display and Benito's decimal display is in the software that we use to program this Arduino Nano so it can program the EEPROM chips. And so we'll spend a bit of time looking at that in this video. So here's this decimal display at the moment showing a value of 247. And as you'll notice, I've added some extra things. So I've added a higher value capacitor here. And I've added some LEDs to these chips so we can see exactly what's happening. And as you'll remember from Benito's videos, we're using a multiplexing setup. So this is a counter. This is a 74HCT161, which is counting through 4 different values in binary here, which you read left to right. So that's the zeros, the ones place, that's the twos place. And so here we have a decoder, 74HCT139, and so that will bring low whichever line this counter is currently selecting. And so what that does is, if we use these 2 bits which are counting from 0 to 3, we can in fact use those as addresses on our EEPROM together with the data in the A register to select a particular value. And so we're selecting which parts of the decimal display should be displayed in each of the positions. So we have the ones position, the tens position, and the hundreds position, each indicated by one of these values from 0 to 3 that this counter is cycling through. And in addition to that, this demultiplexer will in fact pull low one single signal, and so those have been directly connected to the cathodes of all of these displays, and so they'll pull down whichever particular decimal digit display we're actually addressing at any one time with this binary counter. And so the counter itself is just a 555 chip in A-stable configuration with a capacitor between pins 2 and 6, between ground and pin 2, pin 2 and 6 tied together, and then some resistors from pin 6 to 7 and from 7 to 5 volts. And so all of this is explained in detail in Benito's video, so I would suggest you have a look at it to find out the details. Now the first interesting thing that I discovered is, of course, we don't want to read it this way. We want this 555 to oscillate at a much higher speed, just as Benito did. And so he suggested replacing this capacitor with one of a much lower value. And so let's do that. So we'll take out this capacitor, and you'll notice something very interesting. This display is already working perfectly without any capacitor whatsoever here. And so in theory, I would want to put a much lower value capacitor in there, for example this one, but it turns out that that's not even necessary. So with or without that capacitor, I am actually seeing the correct value. So I put this in, doesn't really change much. Now I have slowed the rate a little bit by inserting that capacitor, but the surprising fact that I discovered while building this in the same way, following Benito's instructions basically, is that you don't actually need a capacitor here between ground and pin 2, which surprised me initially. So I decided to draw out the circuit so we can have a look and try to understand why this is actually working correctly with no capacitor at all. So very quickly, let's first look at the entire circuit for the digital display. So here we have our 4 digits, the common cathode decimal digits, and so the cathodes of all these common cathode displays are connected to one of these outputs from the demultiplexer, and the inputs to the demultiplexer come from this counter here, which is cycling through the binary values 0 to 3, and then this demultiplexer will pull down the corresponding cathode so that it will actually be displaying at the moment when a particular digit is selected by this counter. And at the same time, these 2 digits from the counter will drive these 2 address inputs, A8 and A9 of the EEPROM chip. And of course the first 8 bits of the address signal will be driven by the actual value, which will come in from the A register. And so the counter itself is driven by a clock signal, which comes here from our 555 timer, which we somehow magically are able to operate without a capacitor here from pin 2 to ground. So the question now is, how is that possible? How can we have an astable 555 timer without a capacitor here? So if you think about that theoretically, having an open circuit, this is in fact an open circuit, it corresponds to having a capacitance of 0 on this capacitor, which isn't there, because capacitance simply measures the amount of charge that a capacitor can store for a particular voltage. Now an open circuit like this, no matter what voltage difference you apply between these points, you won't be accumulating any charge at all, because there really isn't any measurable electrical field that would be able to store charge. And so the theoretical capacitance of an open circuit is 0. Now capacitance of 0 would mean that whatever this resistance value, the time constant, which is R times C, would also be 0, and a time constant of 0 in fact means a frequency of infinity, so an infinite frequency. And of course an infinite frequency isn't possible in the real world, so there must be something else going on. So let's try and have a look at that and see if we can find some solution by looking at first principles. So here, in this bottom part of the schematic, I've drawn let's say the inside of the 555 timer in a schematic representation. And so the principal part is this voltage divider, which divides the supplied voltage into 3. So these resistors all have equal values. And then 2 comparators, which compare pin 2 and pin 6 respectively to the 1/3 and 2/3 of VCC that this voltage divider provides. So let's just try and reason through this in a straightforward manner. So let's just suppose, for the sake of argument, that this latch is set. And so what that would imply is that this Q signal here is outputting a high signal, and this inverted Q is outputting a low signal. And so if that's outputting a low signal, which is in fact 0 volts, then that would mean that this base of this transistor here is at 0 volts. And of course, so is the emitter, because it's directly connected to ground. And so there's no voltage drop between base and emitter, and so there won't be any current from the base to the emitter of this transistor. And if there's no current through a bipolar transistor, well, then it means that the collector is in fact iced and it's switched off. So this pin is not connected to either the emitter or the base. And so in fact this connection, it's as if it weren't there. That's connected to nothing. So if we sort of think that that's away for a moment, and then what we have here is in fact a large resistance which consists of these two values, which is connected to both the positive input of this comparator and the negative input of that comparator. Now one of these comparators, they don't admit current, or extremely small currents, microamps at the maximum. So we can consider the current flowing into these operational amplifiers as 0. And so if there's no current flowing either into there or into there, then in fact there's no current flowing through these resistors. And so this entire setup is in fact at 5 volts. This is behaving as a large pull-up resistor. So essentially we're setting this positive input on that amplifier to 5 volts, and we're setting this negative input to 5 volts. And so a differential amplifier with a negative input at 5 volts, no matter what the positive input is, that one's going to be off. And so this signal will be low. This will be ground. And so we won't be setting the latch at all, but it is set, so not setting it some more isn't really going to change anything. Now if we look at this amplifier, so that's its positive input will be at 5 volts. And so whatever its negative input is, anywhere between 0 and 5 volts, this amplifier will in fact be outputting a high signal. It will be saturated. And so that will be outputting 5 volts. And so it will be asserting the reset signal as soon as this latch is set. So if somehow this latch ever becomes set, it will reset immediately because of this pull-up resistor. So okay, it resets, then this latch is going to switch state, so the output will become 0, and this inverted output will become 1, or 5 volts. And so if this latch is in the reset state, then this inverted output will be at 5 volts. And so the emitter stays at ground volts, that's hardwired, at 0 volts, that's hardwired to ground. And so we'll have a voltage drop from the base to the emitter, and so we'll have a current flowing through this transistor. And we'll have a pretty large current because this will be a 5 volt drop. And so this transistor will in fact be saturated. And when it's saturated, what that means is that the collector and the emitter are more or less shorted. So there's a very, very small voltage drop, 0.1 or 0.2 volts from the collector to the emitter. And so essentially this node is connected to ground. So we'll have one resistor here, which is sending current from 5 volts to ground. Okay. And then we'll have another resistor here, which will also be connected to ground on this side. And that side, as we know, is going only into these operational amplifiers, and no matter what sort of voltage we're dealing with here, under no circumstances will any current be flowing into these operational amplifiers. And so in this case, that resistor, and this resistor alone, is in fact behaving as a pull-down resistor. There won't be any current through it, and so all these points will be at the same voltage as that point, which is 0 volts. And so they're going to pull these two pins on these operational amplifiers down to 0 volts. And so on this amplifier, what that means is if the positive input is at 0 volts, then no matter what the negative input, this amplifier will be off. So it will be outputting 0 volts. And so it will stop asserting the reset signal on this latch. But okay, it's reset, so whether or not we assert the signal doesn't change anything. But then this amplifier is also going to be, its negative input, or inverted input, is going to be pulled to ground by this resistor. And so no matter what its positive input, it's always going to be larger than the negative input, which is at the minimum, which is 0 volts. And so this amplifier will turn on, so that will be outputting 5 volts. And so it will set the latch. And so what we've just shown is that if at any point this latch becomes reset, becomes 0, then it will set. It will trigger this set signal. So what we have here is a circuit that as soon as it's in one state, it's going to assert the opposite input immediately without any delay. Now, of course, immediately in this case means as fast as this circuit will allow it, i.e. the various components, meaning the latch itself, these amplifiers, and this transistor. And so they'll have whatever their switching characteristics are, but that will typically be measured in tens of nanoseconds, 100 nanoseconds absolute maximum. So far as I can reason from this diagram, what this output here is in fact oscillating at the maximum speed that its components will allow. So very likely, let's say somewhere between 20 or 30 or maximum 50, 60 nanoseconds. And so that corresponds to probably a frequency of, let's say, 5 to 10 megahertz. And so, unfortunately, I don't own an oscilloscope, so I can't actually measure the frequency of the clock signal that this particular setup is generating. But from thinking about it for a slight moment, I would suspect that that's somewhere in the tens of megahertz. So here's a quick look at the EEPROMs that we'll be using in this computer. I'm using 8 kilobyte or 64 kilobit EEPROMs instead of the 16 kilobit EEPROMs that Benita used, mainly because I couldn't find 16 kilobit EEPROMs anymore. So ours are a bit larger. Otherwise, it's the same manufacturer. It's just a larger model. So this one is the AT28C64 rather than 16. And so the biggest difference, of course, is that we have 13 address lines numbered from 0 all the way to 12, rather than the 10 address lines on the 16 kilobit version. Other than that, the EEPROM operates in a very similar way. So we have 8 input and output pins to read or write the data values on the address which we are supplying with 13 different bits. And then we have a chip enable, an output enable, and a write enable signals, and ground and VCC. NC means not connected, so it is actually a 28-pin package, but we're in fact only using 26 of the EEPROM is only using 26 of those pins. Now there are a few other important differences which we will look at on page 5 here of the datasheet, where it shows us how the various operating modes work. So remember when we talked about the RAM chip, that we were able to exploit a feature of the RAM chip whereby we could in fact set the output enable. We could permanently activate that by hardwiring it to ground, because on that chip, as soon as we asserted the write enable, then the chip would basically go into write mode. But for these EEPROMs, we can see that isn't actually the case. So you can see here that if we want to perform a write, we really need a high signal on this output enable. So as soon as the output enable is low, for example in this state, whatever the write enable does, if that ever goes low, then no write will occur. So we have a write inhibit here. And so when we're, that of course that's not so important inside the computer, where we'll only ever be reading the ROM chip, so there we can certainly tie that permanently low. But of course in our EEPROM programmer, which we've built here, we need to take care that we are actually able to control that output enable signal, because we need to deactivate it, i.e. bring it high, if ever we want to write. So that's one thing we need to keep in mind. Now a second thing, which is at least of interest, if you'll go back to Benita's episode where he talks about his EEPROM programmer, there is a particular time, this is for reading, but writing is shown here. So there is a particular write pulse width, which is in fact the time during which the write enable signal goes from high to low, i.e. is activated. And there were some timing constraints on the length of that write pulse. But on this chip, there is actually no maximum value. So in contrast to Benita, who I believe had to make sure that his write pulse was at most 1000 nanoseconds, i.e. microseconds. We fortunately don't have that constraint because we're probably using a slightly more modern version or a later version or whatever it is, but so we don't actually have a maximum value for the write pulse. It needs to be minimum 100 nanoseconds, but it doesn't matter at all if it's any longer. So okay, that gives us a little bit more freedom than Benita had. And so now let's just quickly have a look at the schematic for this actual EEPROM programmer. So as I said before, the hardware is very similar to Benita's design. So we have an Arduino Nano here, and we'll use its digital pins. Most of them are up here. D13 is here to control first of all some pins on this EEPROM. But since we don't have enough digital pins on the Arduino Nano to control all of the bits that we need to control on the actual EEPROM, we're using these two shift registers. And so we're going to output some of the bits that we want to control into the shift register combination first, and then we'll use the rest of the pins on the Arduino so that we'll have the total number of pins that we need to drive the writing operations on that EEPROM. And that's exactly the same way that Benita organizes his EEPROM programmer. So we have the Arduino here, and we have the EEPROM on the other side, which on the breadboard we can just insert in this space here. And so what we need to do if we want to write to an EEPROM chip here, of course we need to control the write enable signal, but as we just saw, we also need to control the output enable signal. We need to control obviously the 8 address lines, so depending on whether we're writing or reading, we'll have to read or write from those. And of course we need to control on our chip 13 address lines. So that's a total of 13 plus 8, that's 25, 26. We need to control 27 different signals. We can always activate chip enable, that won't hurt. But we need to be able to toggle both write enable and output enable. And so, as I just said, what the technique we'll use is to have these two shift registers here. And so what we're going to do is we're going to drive all of the address pins here from the shift register. And so we have two of them, which gives us a total of 16 bits. But of course our addresses are only 13 bits long, so in fact we'll only use the 13 lowest of those 16 bits, and that leaves us 3 here which are not being used for addresses. Now these are shift registers, so the way that a value is written into them is that its output from the Arduino on its digital pin number 2, 1 bit at a time, onto this serial input for the high order shift register. And then there is this shift register clock signal, which the shift register is expecting, which we pulse also from the Arduino on its digital pin number 3. And every time we bring that high and low again, whatever is on the serial input pin will be written to the highest order bit here, and the value that was there will shift over there, and that value will shift over there. So everything will shift to the right by 1 bit. And because we've chained the two together, this highest order bit will in fact go into the serial input for this next shift register. So the net effect is that that bit will in fact move over to here. And so we really are shifting all of these bits up to 16 positions all the way over there. And so since we're starting with that bit, which will end up over there, and then the next bit will end up here and here and here and so forth, we need to in fact shift the bits in least significant bit first. And as it turns out, the way I hooked up my shift registers is actually the exact opposite of what Benita did. So I think he shifts his bits into the serial input in the most significant bit first, and I'm using least significant bit first. But apart from that, same difference. Now the 74HC595 has an extra little feature. So although we can pulse this shift register clock to clock in the various bits in a serial fashion, they won't immediately appear on these output lines. And to make sure that these outputs actually reflect the value which has been shifted in, we need to pulse a second clock signal, which is this register clock signal. And so we need a third pin here, which we can drive from the Arduino. So in fact, we have the D2, which is the data in pin, or the serial input pin. then we have this serial register clock, and then we have the output register clock. And we need to control those 3 pins. But that will allow us to set a total maximum of 16 different bit values on these 2 shift registers. And so we've connected the 13 least significant bits to the address pins on the EEPROM. And then, as we've been saying, we need to have a way to control this output enable pin, because on the EEPROM, we need to have that high if ever we want to write, otherwise it won't allow writing. And so that's connected to the 16th bit of that shift register. So in fact, when we shift out a 16-bit number, the 13 least significant bits of that number will represent the address in the EEPROM that we're interested in. And the most significant bit will in fact determine whether we want to input into the EEPROM, i.e. write, or if we want the EEPROM to assert its the value that's at that address, i.e. we would like to read from the EEPROM. And so we need that 16th bit. And now the 15th and 14th, the bit number 15 and bit number 14 and 13 we're not using. So we can set those, obviously, from the Arduino, but they'll have no effect because they're not connected to anything. And now all of the other pins on the EEPROM, which we need to control, they're connected directly to the Arduino. And so in particular the data pins here, so IO pin 0 all the way up to 7, they're connected to the digital pins number 5 till 6, 7, 8, 9, 10, 11, 12 on the Arduino. And that really leaves us just one extra pin here, pin 13, and we'll be using that to control the write enable signal. And now another interesting fact about this, about the actual Arduino. If you look carefully, you'll see there are a series of LEDs here, and in particular this LED simply reflects the state of the D13 pin. And so, in theory, we'll be writing using short pulses, so this signal should go low for short periods of time, and then it should basically remain high for any other period. And so it gives us a very crude way of seeing if the program that we're running currently seems to be behaving the way we expect, then that LED should be on most of the time. And so if for whatever reason that starts flashing or it appears not to be in a stable or predictable state, well, then we'll have an early indication that maybe something's gone wrong with our programming. So that's a useful thing to know. And also, of course, we'll be using the USB connection from the Arduino, first of all to send programs to the Arduino, but second of all we want to read and write using a serial protocol from the Arduino while it's running its program. And so we're going to need the digital 0 and 1 pins, which are over here, because the Arduino uses those for its communication with the host over USB. And so we're not connecting those, we're deliberately leaving the Arduino. You can see here on the schematic we haven't connected those. Other than that, the only aspect I think of this Arduino programmer which we still need to look at is the actual software which we're going to use to program EEPROM chips. So we'll have a look at that now. So here we have our Arduino development environment, which we'll be using to program the Arduino on our EEPROM programmer. And so this is has the sketch which I've called digital display loaded right now, which is what we use to write the encodings into the EEPROM chip, which will allow us to display decimal values for our A register. But because we'll be using this EEPROM programmer not only for the digital display, but also for the 4 chips which make the 4 EEPROMs which make up our control unit, as we'll see in start looking in the next episode, it would obviously be useful if somehow we could abstract out the let's say the lower level functions of reading and writing and managing the various bits and control signals on the EEPROM, which we need and which we'll need to do in both cases, not only for programming a digital display EEPROM, but also for our control logic or any other use we might think of in the future for our EEPROMs. So it would be nice to have some sort of a repository of the functions, of the base functions that we need to manipulate and to program our EEPROMs using the EEPROM programmer which we built. And it so happens that Arduino actually have a mechanism for that. So if you have a look here at their website, let's have a look in the reference section. You'll see there's a header here, libraries, which is what we're interested in. And so you can, first of all, you can import a library into any sketch. And so if you look very closely, you'll see here that I'm importing a library called my EEPROM. And so my EEPROM is in fact a library which I myself have written, which is specific to the EEPROM programmer, which I've just shown you. And so you can do that using the Arduino development environment. And so we'll have a look what they tell us to do. So there's a tutorial here on writing your own libraries. So we'll have a quick look at that. So essentially what we need to do is we need to write our library as a separate set of files. And so we need a header file, something along these lines. So this tutorial uses a library for producing Morse code. We need to build a header file which is going to define what library features we are actually providing to a program which is going to use our library. And then we need an implementation file which will be the Morse CPP file, and that's going to contain definitions of the various functions. So you can go through this tutorial if you like to understand more deeply how that works. The important part here is to make it play nice and integrate properly with our Arduino development environment. We need to make sure that we place this header and implementation file in the right place. So what you need to do is inside of your sketchbook directory, which is where your Arduino IDE writes all of the sketches, there is actually a folder called libraries. And we can see that on my system. So I have my sketchbook folder open here. And as you can see, these are all my projects. But then there's a libraries folder inside there. And so inside of that libraries folder, you can make a subdirectory for any library which you intend to write. And so I have a my EEPROM folder in here, and that contains the header file and the implementation for my EEPROM library. And so here they go through the example of using a Morse code, and so I've done the same for my EEPROM programmer. So if we have a look at the contents of those files, and now unfortunately, let me just open the IDE next to it. Unfortunately, for some strange reason, you can't actually easily edit or manipulate these files inside the IDE. So this is very good for working with sketches, but you can't actually open that file, or at least I haven't found out how to do that, to open this file inside the IDE. So I just have it open in a text editor here. And so this header file, that's the file which we're including here into our sketch. That in fact defines all of the features which we're exposing to any program that wishes to use our EEPROM programmer. And so the way it's done is we have a class, EEPROM, which is this one. And in fact we have a variable which is of the type of that class, which is in this header file it's declared as an external variable, and what that means is that somewhere in the final executable there will be a variable of type my EEPROM which will be an object which contains all of these functions. And so what that means is that in my code, if I go and have a look at my setup function here, I can write something like that. I can simply write my EEPROM.init, and what that will do is that will look for that singleton object which my library has created and call its init function. Okay, so that's nice. And then we have some other functions that it provides. So we can read from the EEPROM. We can read at some address, which we provide here as a 16-bit number. We can write a certain value, which we provide as an 8-bit number, to an address in the EEPROM, or we can dump everything, the entire contents of the EEPROM, from, or not necessarily the entire contents, but from some start address until some end address. So that's a pretty simple interface, but it's actually all we need, because what the values are that we'll be writing, that will of course depend on the application. So for our digital display, we'll be writing some encoding here of the the graphical shape of the decimal digit which we want to write, but of course for the control logic we'll be writing totally different bytes into particular addresses of the EEPROM. But so that this is how the library is used. So in fact it works very much the same way as the serial library. So you access the singleton object, which contains all of the functionality of the library by writing the name of the singleton object and then a period to say you're accessing member functions. And in the same way, we're accessing the member function init of this singleton my EEPROM, which our library will create. And so here we have an example of this calling this dump function. So I'm calling the dump function, and in this case, I'm dumping all the values from 0 up until this value. So that's how a sketch such as this one can use this EEPROM library. And so that's the purpose of the header file is to define how it can do that and what the features are which we're providing. Now, of course, we need to implement that somehow, and that's what this C++ file is for. Now, since this is a raw C++ file and not a sketch such as this file is, we actually need to include a bit more files here, such as very importantly the Arduino header, and then this is the standard integers from C which we include, because the raw C++ file doesn't do that for us, and so we'd have compile errors. For example, this function comes from the Arduino library, and so this C++ file somehow needs to know where that is. So we need to include those files in our C++ implementation for libraries. You don't usually do that inside sketches, because these, the Arduino IDE, will in fact wrap the contents of your sketch inside of a C++ file, which automatically includes all of those libraries. But so for libraries, that's not done, so we need to do it ourselves. And that's what those include statements are all about. But then we come to the actual implementation of the read and the write functions for our EEPROM programming. And so if you remember from looking at the schematic, first of all we need to interface with these two shift registers. So we have the data signal here, which is actually going to be on the pin 2 of the Arduino. And then we had the shift register clock, which we will manipulate through pin 3 of the Arduino. And then we'll have the storage register clock, which we need to pulse one time at the end after having shifted 16 bits into the shift register. And so that we've connected to pin 4 of the Arduino. So I've just defined these constants so we can use them in our routines when we're actually going to implement the fact that we need to shift these bits out one by one, and then shift this clock, and then we want to pulse this storage clock at the end. And we've also defined constants here for the 8 data pins. And then finally, remember, we've attached the write enable signal of the EEPROM directly to pin 13 of our Arduino. So those are just some constants to make our life easier when we're writing code. Now these constants, in fact, those are parts of the 16-bit address. So remember that the 16-bit value which we write to our shift register, the 13 least significant bits of that will represent the actual address in the EEPROM, but the most significant bit, which is represented in hexadecimal by this 8000, that's the most significant bit of a 16-bit value, so it's in binary, it's a 1 with 15 zeros. That is in fact the value that should go into the output enable pin. And so if we want to read from the EEPROM, then the output enable should be low, and so that 16th bit should in fact be a 0. And that's the reason I've defined this mode read as a 0. And that 16th bit should be a 1 if I want to write, because then I don't want to assert the output enable pin on the EEPROM, and so I'll want to have I want to keep that high because it's an active low. And so the mode write constant has been defined as a 1 in that 16th bit position. And so what we'll actually do, we can have a look at that function. When we're going to select an address, the function that we provide here for the rest of our library is going to take an actual address, and it will then OR that with the mode. And so it will either in addition set or not set that 16th bit of the address. Now of course, if for whatever reason I use this function in a bad way and I have an address in here which already has the 16th bit set, then that would imply that we're in writing mode, If I wanted to read from such an address with the 16th bit set, well, it's not going to work, obviously, because this OR, even if mode's 16th bit isn't set, this one would be, and so the output enable will be high, and so we won't be outputting. But that's acceptable because you know, we're going to be the only ones, and this is a static function, so it's really only used by the other functions inside this library. So we in principle, we have control over what's happening here. So that shouldn't be too much of a problem. And of course, our EEPROMs have addresses which are maximum 13 bits wide, and so we really shouldn't be using any address value which is more than 13 bits in here. So okay, we might have a slight possibility of optimization here, but we haven't done it because I don't think in this case we'll have many problems because of that. Now, when we select, when we build our 16-bit value, which we want to shift out, then of course we actually have to perform the shift, and so that's what this function is all about. So we're actually going to take the address ORed together with this mode, which will set the 16th bit of the 16-bit value, which we're sending out to the shift register. So our shift out function here will first of all we'll set both of the clock signals low, so the shift register clock and the storage register clock. And then, of course, we need to shift out the 16 bits of this value with the least significant bit first. And so this shift out function is something that the Arduino library provides, and it shifts out 8 bits, so one single byte. And since we need the least significant bits first, we're going to get the least significant byte from that value. So that's why we're ANDing it with the 8 least significant bits here. So we'll send out that least significant byte first with one call to shift out, and we'll be using this data pin, which we defined as pin 2, and we'll be pulsing the shift register clock, and then we'll be doing the same for the high order bits, high order byte. So the high order byte, we can obtain that by taking the value, shifting it 8 positions to the right, so that the high order byte goes into the low order byte position, and once again make sure we only take those 8 bits. And so once we've done all of that, once we've shifted out in all of those bits into the 2 shift registers, we need to remember that we should also pulse the storage register clock once, so that the output pins on the shift registers will actually show the new value which we've just clocked in. And so we do that with this short pulse function, which will simply bring the clock high and then low again. So once we've selected an address using this shift out method here, so we will have set the 13 bits of the address, and we'll also have set the output enable pin on the EEPROM controller. Then of course we need to make sure that the I/O lines, which are connected directly to our Arduino, are in the correct input or output mode. And so we do that at the same time when we select an address, since we know if we intend to be reading or writing. And so the set I/O pin mode simply loops over all of the data pins and sets them either in read or write mode. So that's also a function which the Arduino library provides. So that's our select address function, which we'll use for both reading and writing. We'll tell it what we want to do in this mode parameter. And so here we have the implementations of the actual public functions which we're interested in. So if we want to read from the EEPROM at any address, what we'll need to do is first of all select the address, and we'll need to set the output enable pin such that we're actually in read mode. And of course that will also set our data pins to the correct mode. We have a short delay here because the EEPROM chip itself needs a little bit of time after the address lines have been asserted to start outputting the correct value on its data pins. And so then we just read them one by one. So we're going to go we start with a value of 0 for our byte which we're trying to read. And so we'll go through all of the different bits, and so then we'll perform a digital read on each one of the bits which are connected directly to our Arduino. We'll check if it's high. If it is, then that means we'll have a 1 in that particular bit position. So that's a 1 shifted left by whatever bit we're reading at the moment. And so we need to OR all of that together into the result. And so the result will contain the binary value which is asserted by the EEPROM on the various data pins. And so this function in fact just returns that value, so then we can do something with that in our sketch, because this is the library which we'll be calling from our sketch. And similarly, we provide the write function. So the write allows a sketch, which is using this library, to write a value to the EEPROMs at a particular address, which we provide in this input parameter, and then the value is the 8-bit value, which we provide here. So once again, we need to set the correct address, so that means writing everything into the shift registers. So we have a function to do that for us, and that includes the value which we want on the output enable pin of the EEPROM. So in this case, we'll be writing. And then what we need to do is we actually need the Arduino to assert the correct bit value on each of the pins so that we can write it into the EEPROM. And so the first thing we need to do is we need to perform all the digital write operations on the various pins, on the various data pins. And so the value that we're going to write on each of these pins, it depends on whatever position, whatever the bit is in that position in our input value. So the way we do it here is we actually go through all of the pins sequentially, and so we get the value and 1, which is binary 1, which means the least significant bit. We set that on whatever pin we're accessing at the moment, and then we just shift the value to the right by 1. So the next time we come into this loop, we'll be setting the next bit, and then we'll be setting, so first we'll be setting bit 0, then bit 1, then bit 2, etc. So in effect, we're destroying the contents of this value, but we don't need it after that. And since this is passed by value, the caller function won't suffer from this operation. So once we've asserted the correct bit values on all of the data pins, then we need to delay a little bit, and we need to perform a digital write. In fact, we need to pulse our write enable signal on the EEPROM. So since it's active low, we need to bring it low for a certain time and then bring it high again. So here I'm bringing it low for 1 millisecond, and as we saw when we looked at the data sheet of the EEPROM, it doesn't really matter on this EEPROM. So I found that these values, 15, 1, 15, they appear to provide reliable results. So I'm able to write data and read it back and find the correct values. And they sort of perform everything in a reasonable time. So it's a compromise between speed and quality, let's say. So I don't know, maybe if you were to be using some other EEPROM chip, you might find that some other values here provide you with the correct results. But these seem to work very well. And so that's how we perform the write. So we pulse our write enable, and then that's the end of the write operation. Now we provide a small init function here, which any sketch which would like to use our EEPROM library should call before it does anything. So that's just going to set a few pins to the desired pin mode on a certain number of pins. We're also going to bring the write enable high because it's an active low, and that means we won't be writing as soon as we can. And then we're also going to set the pin mode, which is always output for these 3 pins which we're using to control the 2 shift registers. And then finally we have the dump EEPROM function, and so all that's going to do, it's actually going to use its own read function here, read EEPROM, which is the function that we just looked at. And it's going to simply read starting at the start address and then ending at the end address, and there's a little bit of logic in here, a little bit of logic in there to make sure we start on same addresses. So we're always reading 16 bytes at a time, and then we just write those out onto the serial interface. So we're going to use it in a string print, formatted print, and we'll print into there sort of 4 hexadecimal digits for the address. And then we'll be outputting all of the 16 bytes on a single line. And so we'll be doing that for whatever start and end address that the calling sketch has requested. And that's basically the contents of our EEPROM library. So those are the 4 public functions which we provide: the dump EEPROM, init, write, and read. And so now we can write different kind of programs here, which we can use for programming our EEPROMs for different purposes. And we can concentrate on the logic of what we want to write to the EEPROM rather than the mechanics of dealing with the shift registers and the pins on the EEPROM and making sure the write operation itself succeeds. And that's the advantage of pulling all of that out and putting it into a library. It means we can use it in all kinds of functions. So now let's have a look at the actual digital display sketch here, which uses our EEPROM library, which we've just looked at. And so what it needs to do is it needs to just fill the EEPROM with correct encoding values, so that the binary value which is in our A register can be shown on the digital display. And as we saw when we looked at the circuit that does that, what we really need to do is our EEPROM will be using 10 of its address lines, so the 8 least significant bits of the address will be used simply to represent the binary value which we want to display, and then the bit number 8 and bit number 9 of the address will be using to cycle through the different actual digital displays that we want to use. So we'll be using the one which is furthest to the right to display the ones place, the second one to its left will display the tens place, and the third one will display the hundreds place. And so essentially what we need to do is calculate the particular address at which a digit needs to appear, and then we need to write the correct encoding, and so the value which is stored at that EEPROM will be driving the different parts of the 7-segment displays. And so here, first of all, I've defined this array digits, which is an array which goes from 0 to 9. So each part of each byte in this array represents one digit. And so, as you can see, it's defined as a bitwise OR of a series of graphical elements which together will make up a 0. So for a 7-segment display, if we want to display a 0, we need to display the horizontal top bar, the horizontal bottom bar, the vertical left top, the vertical right top, the vertical left bottom, and the vertical right bottom. And so those together will form a 1. And so each of these constants, in fact, corresponds to a single bit position in the actual byte value which is stored in the EEPROM, because each one of the output pins of the EEPROM is connected to a particular segment of the 7-segment display which we'll want to show. And so in my case, the way my digital display circuit has been built, in fact my horizontal top is connected to output bit number 5 of the EEPROM, and the middle horizontal line is connected to bit number 7, and so on. So you can see that very easily if you're building one. Of course, you can use a datasheet and try and work out all these A's and B's and whatever it is. That's the way Ben did it. But so in my case, I was a bit more lazy about things, and so I simply hooked up one by one each of the output bits of the 7-segment displays and discovered which bit position in my EEPROM that I would connect it to. And so now I can very easily define all of these let's say, graphic symbols for each of these digits by simply ORing together the various bits of the segment, or the various segments which I need to display in a 7-segment display. For example, the 6 here is basically this combination. And so what that allows me to do is here I have my main function, which will write all of the display digits. I can do either signed or unsigned. So if we're not doing signed digits, so we're doing 0 to 255. So if we're not signed, then we'll be taking 0 to 255. We'll be starting in our EEPROM, so we're not signed, so we'll be starting at address 0. And so here is just some serial output, which allows a person who is monitoring this program running on the Arduino to see what's happening. So we're writing the ones position. And so we're going to go through all of the values from min value, which is 0, until 255. And we'll write to the EEPROM at an address which corresponds to that value. So in our case, it's never going to be below 0. So we'll always be writing 0 plus value. So we're basically at that particular value for the ones position. Remember, we're writing the ones position. The digits of its rightmost digit. So we're doing a division modulo 10, and that's going to give us what the least significant digit is of our decimal representation of the value. And so we read that out of our table here. So this table is going to say, okay, when the start address, which is coming from the A register, has a particular value, and modulo 10 will give us the rightmost decimal digit, then we can figure out which byte we want in the EEPROM by simply reading in this table the different graphical segment positions which we want to light up when that value is coming in on the address lines. And so that value we then write into the EEPROM. And so for every 10 values which we're writing, I simply point out a dot, and so the result of that will be that we'll see a progression of the writing operation on the serial monitor for our Arduino. And then of course we come to the tens position. So for the tens position, we don't want to start writing at address 0, but we want to start writing at address 256, which is in binaries 1 with 8 zeros. So that means address bit number 8 is set to 1. So that's when our counter is looping through 0, 1, 2, and 3, this is the value 1. And in that case, we need to get the correct value onto the 7-segment display, which represents the tens position. And so what we'll be writing in there is the value we're interested in divided by 10. And then once again, we need to take the modulo of that by 10, and that will give us the digits for the tens position. And so we need to, again, find the graphical representation of that digit in our array. And of course that's the same, because the tens position or the zeros position for a digit is the same. Our digits are all the same. And so we write that into that address. So the address, of course, plus 256 in this case, goes into the EEPROM. Now here is a little optimization. So if our value is below 10, then we don't actually want anything to appear on the tens position, because the value is smaller than 10. We could have a 0 there, but then we'd have values like 0, 0, 5, and I just prefer in that case that the digital display should show just 5. I don't want to actually show a 0 in the tens position. So if it's smaller than 10, we should write nothing, and so nothing means none of these graphical elements will show up. And so that's of course distinct from 0, because 0 will actually cause all of these segments to light up, and we don't want that. We want nothing to light up. But if it's larger than 10, specifically, for example, if it's 102, then of course we do want a 0 in the tens position, and so that's what the purpose of that if statement is here, is to make that distinction. And so again, for every 10 digits that we're writing, we'll show a bit of progress on the serial monitor. And then we come to the hundreds position. And so for the hundreds position, same trick here. So if the hundreds digit, if we're at a value below 100, so any value up until 99, we don't want to show anything in that position. And the address we're using in this case is hex 200, so that corresponds to the 9th bit, address bit set to 0. So that's counter position 2, 1, 0 in binary, so that's the hundreds position. And if we are actually over 100, well then we want to write out that particular digit. And so here we'll be calculating the division by 100 in this case, and again modulo 10. Now in principle that's not really necessary, because our value should be below 256, and so modulo 10, or the value itself, should be the same, but it's good practice to guard yourself against misuse of the function. Perhaps at some point a value of 1000 for whatever reason might sneak into there, and that could break the function, and so that's it's a form of defensive programming basically. So right, that's for the hundreds position. And then for the thousands position, if we're writing unsigned values between 0 and 256, we won't actually ever be writing anything. So those will pretty much be hardwired to 0, as you can see here in the case of non-signed. Oops. In the case of non-signed values. Now for signed values, my EEPROM is actually programmed to also support signed values, and the way we determine if we're using signed or not signed is we're going to use the bit position number 10, and so that's why we have this start address calculation here. So that's a 1 followed by 10 zeros in binary. We could use that 10th bit to specify if we want to have a signed or an unsigned representation. But in my computer, in the end, I've actually hardwired bit 10 to ground, so that's always 0. And that means unless you actually remove that wire and put a switch in there, or temporarily sort it to 5 volts, you won't actually see any signed values. But the codes are in the EEPROM, so the code here does support it, because initially I thought I would build in a switch there, but it turns out that most of my examples use unsigned values anyway, so I just haven't got around to that. But anyway, the code is here, so we can actually write it out. And so that's why we have these tests for whether we're dealing with signed or unsigned numbers at various points in the code. And so if we are dealing with signed numbers, well, then we want to go, of course, from a value of minus 128 until plus 127, rather than from 0 to 255. And so then our address is a little bit different. So first of all, we're going to write those, we're going to set that bit number 10 to 1 for such addresses. And so we add that to whatever address we're calculating here. And once again, if the value is smaller than 0, we also need to add an additional 256, because in 2's complement representation, the value minus 128 actually starts after the value 127. So the unsigned value 128 is the same as the signed value minus 128. That's how 2's complement works. And so that's why we need to add 256 here for because 128 minus 128 is 256 for values which are below 0. Other than that, we do exactly the same, and so we write the ones position, we write the tens position, we write the hundreds position, and then of course the thousands position, which in fact is the sign. In the case that we're dealing with a negative value, and if we're in the signed range, address range, well, in that case, we'll simply write a mid-horizontal line, which corresponds to the minus sign for negative values. So that's basically the code which I have here to write the correct value, correct codes into the EEPROM. And so in our setup function here, as we discussed before, we need to initialize the EEPROM library. And then we can just write all of the digits, first of all the unsigned digits and then the signed digits. And we can dump out the contents of the EEPROM once we're finished. But since I don't always want to do that, I've protected that here with a little conditional define. So at the top of my file there's a dump constant here, which I can set to 1 or 0, depending on whether I want the contents of the EEPROM to be shown on the serial monitor after it's finished. So we'll just leave that at 1 for now. And then a final protection which I've built in, which you'll see here, is that as soon as the program starts, I don't immediately just go ahead and write into the EEPROM. And the reason for that is that this hardware programmer which I've built is of course only powered when it's connected to the computer via its USB cable, because the power for the breadboard comes from the Arduino, and the Arduino is only powered if it's connected to the computer. And the result of that is that every time you unplug this programmer and plug it back in, even if you switch EEPROM chips afterwards, it's going to start the program again. So as soon as you upload the program into the Arduino, it stays in there, and as soon when you power it off and you power it on again, it will just start running that program from the beginning. And of course, we don't necessarily always want it to overwrite an entire EEPROM as soon as you plug it in somewhere. You might not know what particular EEPROM was there, or you might not remember which program is currently inside the Arduino, and so generally that doesn't seem to be a very good idea. So what I have here is a little protection which I've built into all of my EEPROM programs, which simply checks. So it does a serial read, and it expects the user on the serial monitor to really enter a Y as a yes to start the process here, and if he doesn't, then nothing will happen. And so that's been very useful, because it means that when I freshly plug in the EEPROM programmer with some chip which I don't remember, or some program which I don't remember, I have a chance to say no and make sure the correct program is uploaded before I go ahead. And so now we understand how we can use this EEPROM programmer and the software we wrote for this Arduino Nano to program EEPROM chips, such as this one, which we're using to display values in a decimal representation here from, in this case, the A register. And we can use that same EEPROM programmer to program any EEPROM chip by writing the software for this Arduino. And so what we're going to start looking at in the next episode is in fact the last component of this computer, which we haven't looked at yet, and that's the control unit over here. And so the control unit on this program is basically implemented by 4 EEPROM chips. And so most of the hard work is in fact in the program, in the software, which we'll be using to program those EEPROM chips. And so what the control logic needs to do is it will get its instruction from indirectly from program memory through this instruction register, and then it will use the encoded instruction to then drive all of these control signals, which will in fact coordinate the operation of the rest of the computer. And so since that too is largely based on these EEPROM chips, we'll of course be using this same EEPROM programmer and the same EEPROM library that we looked at today. So we'll start looking at that in the next episode. See you then.